Good morning, everyone. I hope you have a good rest last night, like me. I don't know why the screen seems to be squeezed a little bit. Maybe everyone has been very health conscious these days with a narrow screen and the wider screen. So this morning's first part of the talk is related to the first part of yesterday afternoon's talk. I was talking about multi-objective ensemble learning. Yesterday, then I explained a little bit on the multi-objective evolutionary algorithm, especially when the number of objectives increases, what can we do? So today, I'm focused on class imbalance learning, especially using ensemble approach. So the first part, introduction, overlaps with the introduction yesterday. I'll go through it more quickly today. So introduction, as I said, I'm focusing on class imbalance learning, especially for classification. For most machine learning methods nowadays, especially the first time, suppose a student new to the area, they have some kind of implicit assumption when they apply one algorithm to a particular task. First implicit assumption is that every class in the training data set has the same misclassification cost. I just think of this loss function or error function you have seen in most of the literature, in most papers. And second, the implicit assumption is the overall accuracy is the goal. We want to maximize the classification accuracy. In terms of classification accuracy, we normally measure it on a testing data set or sometimes called a validation data set. But sometimes these two assumptions do not hold because of misclassification on one class might carry higher costs than the other class. Secondly, this class distribution might be different. So this is what we are very interested in tackling the problem in unbalanced or imbalanced class classification. So class imbalance learning, as I mentioned yesterday, we are looking at classification problems where the data distribution is highly skewed. We have a minority class, we have a majority class. I'm going to mention a little bit, actually, there are more complicated cases. We have a multiple minority classes, multiple majority classes. Then things get more interesting. The challenge here is to improve the performance of the classifier on a minority class. Majority class in comparison will be slightly easier. However, if we just focus on a minority class, we might overfit. So it's very important to improve the performance on a minority class without sacrificing the performance on a majority class. So here's an overview in terms of class imbalance learning. Lots of paper class imbalance learning, both from a machine learning algorithm point of view, as well as from applications point of view. If you take one step back and look at the overall approach they use, they fall into these three categories. First one I mentioned yesterday, resampling techniques have been used extensively in class imbalance learning. We can oversample a minority class or undersample a majority class to make this class distribution to be even before we apply any machine learning algorithms. Okay, so as I said, I changed the problem a little bit. However, when we oversample minority class, we are running a risk of overfitting. You can just imagine. If we undersample majority class, we are running a risk of losing some information because some of these useful data samples will not be used in learning. The second class of machine learning method in dealing with class imbalance problems is called the cost-sensitive method. I think yesterday there was one question asked, if you have an imbalanced distribution within a training data set, is it possible to assign higher weight to the minority class examples to make minority class examples more important in training? Or can we assign a weight in the loss function to the misclassification of minority class? Okay, that's one way in dealing with the class imbalance learning. I'm going to emphasize minority class more, both in terms of sampling the training examples as well as in the loss function. The advantage of doing cost-sensitive methods, then you have to come up with a precise weight to balance between the majority and the minority class. Where do you get the knowledge to set that weights? So that would be a challenge. Very hard to quantify the cost in practice. The last category in terms of methods tackling class imbalance learning is to develop specific algorithms. In this case, ensemble learning has been found very effective in comparison with other approaches. So I'm going to focus on these two methods for this talk. One is the sampling method in combination with these class imbalance ensemble methods. So I explained quite a lot why I always prefer ensembles. I'll skip this slide since it's almost the same argument as I mentioned yesterday. I think Christos asked me a question about the ensemble. I have one formula. This is the simplest ensemble method. This little O of I indicate the individual classifier's output, and then the entire ensemble output can be a linear weighted sum of the entire ensembles. If you have classification problems, then we can use a majority voting in this case rather than using a weighted sum approach. It's still a research area in terms of how to form ensembles given a number of base learners. But there are many different ways. There are many actually different ways to determine or learn this W. As a matter of fact, whenever people talk about ensemble learning, it's really talking about how do you get this W. You can use a linear algorithm to set W very quickly. You can use nonlinear method to set this W, which is more interesting but computationally more expensive. If you look at all these different algorithms, they are all related, but all have kind of format like this. These are very popular methods like bagging, boosting, negative correlation learning I mentioned yesterday. So that's a very quick thing about ensembles. The other thing I want to repeat a little bit is the importance of diversity. I mentioned the diversity yesterday. If you are interested in ensemble learning, you ought to be interested in diversity. If you take diversity out, there's nothing about ensemble learning which is interesting anymore. Okay. Assuming you've been persuaded by me a little bit yesterday afternoon, this morning for the first few minutes, ensemble is interesting. If I'm interested in ensembles, we ought to look at the diversity. Now, if diversity is so important in class imbalance learning, we want to find the relationship between the diversity and class imbalance learning performance. Okay? So we are going to look at it a little bit closer in terms of the role of diversity in this ensemble. So we can carry out in this quite a lot of computational study, running designed experiments, instead of to come up yet another algorithm. This is really try to understand the problem. We can discover very strong correlations between diversity and the generalization performance for class imbalance. In particular, we can show diversity has a positive impact on the minority class. And you say, why is this interesting? This is very interesting. It's a bit like I'm interested in the performance of minority class. Then I'm looking for factors which have the most impact on the minority class. Now, through this experimental study, we discovered in terms of ensembles, this diversity is a bit like a knob I can tune. If I tune the diversity up, so to speak, and I can get better performance for the minority class. So this is sort of the first piece of news. The second piece of news is in terms of overall performance, because we worried about potential overfitting to the minority class, we have to look at the overall performance. This diversity was shown to be beneficial to the overall performance, either in terms of AUC or G-means. The reason we use AUC and G-means in this case is because accuracy is not very good performance measure for imbalanced class. Okay. This AUC and a G-mean, a geometric means, is actually much better performance, especially if you have a highly skewed data distribution. So this discovery actually shows if we can do something about the diversity, we should be able to get better performance for class imbalance. So this work is really like a preparation, saying what kind of factors we can operate on such that we can get a better performance for the minority class as well as for the overall class. So the first idea is called ADA-boost.NC. This ADA-boost is a very popular algorithm. I think some of you might have used it, or at least have heard of it or learned it in class. NC here means active correlation. You know, for the ADA-boost, I just repeat this idea. Now, in case you ever heard of it, if I'm going to build an ensemble to solve a machine learning problem, what I can do is I can do the following sequentially. I train the first classifier, whatever algorithm, let's say I train the first neural networks using backpropagation regime. After I train it, given this particular training data set, some of them will be correctly classified, some of them will be wrongly classified, right? Now, based on this result, I'm going to construct the second training data set. All those examples which were misclassified will be put into the second training data set. For those which were correctly classified, I also sample some of them, inputting the second training data set. So I construct the second training data set. All the misclassified examples will be there. Some of the correctly classified will be there. So I have a second training data set. Then I train the second neural network using the second training data set. Okay, I get the second. After this, there will be some training examples which will still be misclassified, both by the first neural network as well as the second neural network. Right? So I put these examples into the third training data set. So I'm constructing the third training data set. There will be examples which is correctly classified by one of the first two neural networks, but misclassified by the other. I take these examples also into the third training data set. And then I also take some of the examples which were correctly classified by both neural networks to construct the third training data set. And then I use any kind of training algorithm to train the third neural network. It's an ADA-boost. So you can see ADA-boost has two characteristics. First characteristic, I'm going to construct base learners sequentially, one by one. Secondly, I construct the next neural network by reconstructing a new training data set. Within that new training data set, I always emphasize the misclassified examples. Misclassified examples always in the next one. So this is what ADA-boost does. There are actually very good papers, especially in statistics, to demonstrate that this boosting method is actually very, very effective. So what we do is to modify this process a little bit, especially when sampling these misclassified examples. The .NC part is I'm going to increase the diversity in training. yesterday I mentioned diversity in the error because I showed actually one formula to demonstrate negative correlation. The essence is in error negative correlation. Today's example here, AWS.NC, I'm going to introduce diversity in terms of training data samples. So if you look at what we said, the diversity is introduced into the weights of training samples. In the traditional ADA boost, the weight will be given to misclassified examples. In this case, I say, wait. In addition to misclassification, I want to consider imbalance as well. For examples from the minority class, I'm going to increase the weight. For the sample from the majority class, I'm going to reduce the weight. So that's the second term, we call it the ambiguity term. We put into the sequential training of the ADA boost. So it's a very, very simple scheme. Okay, just in the weighting process, we consider imbalance ratio. Very surprisingly, this is probably just a few lines change in terms of the algorithm. We can get significant better performance on the minority class. Okay. You say, why? What's the intuition behind it? Well, instead of putting weight into a loss function, for example, we have this stochastic weight when we sample these training samples based on this imbalance ratio. If it's coming from the minority one, I'm going to emphasize this example more. So both high classification errors and the high diversity will lead to a larger weight. So this actually leads to the outcome. I won't give you actual outcome. I don't have actually the slides, but slides basically I was looking for was a comparison table in comparison with other class imbalance methods, how this AWS.NC can perform better in terms of improving minority and overall performance. Let me skip this part. This multi-class imbalance learning. Oh, sorry. This is different from one. So this multi-class imbalance learning basically indicates there are more than two classes within class distribution. I mentioned just a few minutes ago. For a multi-class classification problems, I might have multiple minority classes and then multiple majority classes. So this description is very inaccurate because if I were four different classes, which one is minority, which one is majority is always with respect to the rest of it. I might have one class in a multi-class classification problem. For the smallest class, it would be a majority. For the large class, it might be a minority. How do we handle this situation? So the first reaction, when this work was first started, and then there was a lot of suggestions saying there is no point in looking at multiple class classification because you can always convert a K-class classification problem into K+1 binary classification problems, right? You can just decompose saying that if I take class, you can always transfer into class 1, not 1, class 2, not 2, and then you can also decompose into a number of binary classification problems. One disadvantage, very big disadvantage of doing this kind of a decomposition is you make this class imbalance ratio even worse. So you probably don't want to do that, although you can get around this multiple class classification problem. It might not be a very good scheme. So this is, I mentioned, the most existing algorithms are designed for two classes. If they look at multiple classes, they decompose into multiple two classes. But these methods are not very effective especially the number of classes are slightly larger. We have a 5 or 6, for example. So the first step is what I did previously is we want to understand the nature of the problem a little bit more before we develop any algorithms. We want to understand if the number of classes increases in class imbalanced learning. Do we encounter any additional difficulties, or are we actually facing similar research problems as before? If the similar as before, then maybe it's a bit of engineering challenges we have to overcome. Otherwise, there might be something deeper we need to think about. So we divide the scenarios into 2 extreme cases. One we call the multi-minority scenario. The other one is a multi-majority scenario. It's academically. So multi-minority scenario is a bit like I have multiple classes, and then for one class I have lots of examples. For other classes I only have a few, so multiple. So I think this might be corresponding to real-world cases in fraud detection or fault detection. You have one majority class represent normal cases, and then you have multiple types of faults. Each one you have only a few examples. So this is one scenario. For a multi-majority scenario, is I have a multi-class classification problems where I only have one minority class. That means for that class, I only have a few examples. For other classes, I have lots of examples. I haven't think of a real-world case to correspond to that one yet. Please suggest to me if you have. But theoretically, I can look at these 2 extreme cases. One is a multi-minority class scenario. The other one is a multi-majority scenario. So the question we want to answer is whether there are any research challenges, different research challenges between these 2 scenarios. Whether these 2 types of problems in essence is the same type or actually different types. Once we gain a better understanding nature of the problem, and then we want to explore whether this very simple idea I mentioned to you at the beginning, A double stop and C, can be applied to multiple cases as well. Because from this description I mentioned here, it does not seem to rely on particular class, because I was talking about only minority classes and majority classes. We did not indicate anywhere in this description how many classes there are. So there might be an opportunity we can apply this A type bootstrap and C directly to multiple classes. Okay, so that's a research question we want to answer. So skipping a lot of computational studies in terms of a computational experimental setup in terms of results, here's the summary of the result. The first conclusion is when we increase the number of classes in a multi-minority scenario, it reduces the ensemble learning performance significantly. You cannot just ignore this issue. Interestingly, previous effective sampling methods will not work when the number of classes increase. So there might be some very interesting theoretical work to be done here, but we haven't done any theoretical work, but experimental observation is very clear. If you rely on sampling to get a better performance when the number of classes increase, that will not work anymore. The ensemble performance is also suffered very significantly for the case of a multi-majority class scenario. So you have 2 scenarios, one have a multiple minority class, the other scenario has multiple majority classes. And then when you increase the number of classes under both scenarios, the performance of ensemble learning dropped significantly. So the key message is first is a summary in terms of the number of classes does have a negative impact on the performance. The second one is somewhat unexpected. If we look at this multiple majority scenario and multiple minority scenario, computationally it shows if you have a classification problems where you have only one minority class, multiple majority classes, these type of problems tend to be much harder than the other case where you have only one majority class and multiple minority classes. Kind of strange. We don't really fully understand why, but this is the observation from quite a lot of the experimental studies of different data sets and using multiple ensemble learning algorithms as well. So if we still want to use sampling, either oversampling or undersampling is satisfactory. Then you say, why? It's just a simple increase of classes. It shouldn't matter. But you can just think a little bit without for me giving you all this result. Doing sampling is always relative. If you have two classes, you can oversample the minority such that these two classes distribution will be similar. If you have multiple classes, okay, some of them are very large, some are very small, some are somewhere in between. For those somewhere in between, how do you do the sampling? You can imagine if you were that class. Were you trying to do a bit of undersampling in order to be more balanced with this minority class, these smaller classes? Or are you trying to do a bit of oversampling in order to be comparable to the majority class? So when you have multiple classes, this sampling seems to be dragged into different directions. So that's actually the intuition you could use to try to understand why this sampling method will not work effectively when the number of classes increase. Right. So given that observation, although I show using only a couple of slides, it's actually built upon quite a lot of computational studies. What kind of solutions we come up with? So the very first solution, surprisingly, is what I just mentioned, A-boost NC. Because A-boost NC, when we introduce negative correlation, is introduced in assigning the weights to the training example. So what we can do very easily is to relate that weight to the class imbalance ratio. Class imbalance ratio basically is a bit like a percentage of this class distribution within the training data set. And then you can use that as a factor to determine the probability of sampling a training example and putting into the next training data set. So it's a very simple scheme which enable you to deal with different classes. So the second approach is a very simple scheme, try to move away from this very traditional thinking. If you have an imbalanced class, the first step is try to make it more balanced, and then apply a machine learning algorithm. And then we were thinking, is there any way we can mix these two processes into one algorithm? We don't have an explicit sampling method, and then have a machine learning. Okay. So this is a somewhat unorthodox method. Let me explain this embedding sampling into learning. The method, we call this DYS. Try to get people to think you can imagine this kind of dynamic sampling scheme. It works in a very straightforward method. If you think of algorithms, it's going to be a very small modification to your favorite algorithm. Whenever you pick up one training example from a training data set, no matter what algorithm, right, you have to go through the training data set. when you pick up one training example, you ask yourself the question, do I really want to be trained by this example? And you say, well, what do you mean ask this question? Well, basically say, I want to calculate the probability. According to that probability, I'm going to use that sample to train my classifier. Then you say, okay, well, that's what you want to calculate the probability. What probability? I want to calculate this probability such that this probability is influenced by the imbalance ratio. Okay, so this is for the samples which were misclassified. Of course, I want this example to be trained. I want to use the example to train the classifier because previously it was misclassified. I want to make my classifier to classify this sample correctly. So every previously misclassified sample will be used to train the classifier. For the examples which were correctly classified, we still wanted to be trained with a probability. How was that probability determined? It's determined by imbalance ratio. Those coming from minority classes will have an increased probability to be selected for training, even that example was correctly classified already. For those coming from majority classes, that probability will be smaller. And you say, oh, that's very simple. Kind of makes sense. Have a question?
Yeah. So that's so does this work for the previously mentioned multi-minority and multi-majority? So that's the other case of really the exercise more of those majority classes.
Well, I don't have a formula here. So we first calculate the so-called imbalance ratio. Assuming I have three classes for simple case, right? And then the imbalance ratio might be 0.7, 0.2, 0.1, which indicate that three classes, 70% will be one class, the largest class. Second class will 20% we have, and then last class only 10%. So imbalance ratio, very simple calculation would be 0.1, 0.2, 0.7. And then we use this number to determine the probability. That's a factor. Yeah. So in this case, I think if you have a 0.1, and then we invert it, we get a higher probability for this example to train the classifier. When you have a 0.7, we assign the smallest probability to train sample. So it doesn't really matter how many classes you have now. We just use this imbalance ratio when we call it train. So it's only a few lines difference. So we don't have an explicit sampling anymore. It's implicit is because we use this imbalance ratio to influence probability. So although you go through training example or iterations, not all examples will be used for training. Depends on probability. Okay. So this handles multiple classes very easily. We can just calculate this imbalance ratio, and then we use imbalance ratio for defining probability. So we don't have to really worry about for a particular class, whether it should be oversampling or undersampling. This is done probabilistically, it's not deterministically. And then it is really applicable whether you have multiple minority classes or multiple majority classes. The writing program is very simple. So that's a very quick description. I think my emphasis is on multiple class imbalance. Because for the binary classes, there are very good methods already. And then we can actually demonstrate that if you use this particular simple algorithm I mentioned, it is better than decomposed multiple class problems into multiple binary class problems. Now, next, I'm moving on this online case. Online case, let me explain a little bit the meaning of online, because different people have very different definitions of online learning. In my case, I'm assuming I receive a data stream. Okay, so there's no set of data anymore, the data stream coming in. But every time step, I get one data example. It's very important that we get one data example. At the next time step, the previous data all disappeared. We cannot use previous data to update my current classifier anymore. So there are two very important factors. One is a data stream, but every time step, I only get one data point. And that's available to me to update my current classifier or machine learning. All the historical information disappears. So this is actually you can say it's a setup, you can also say it's assumption. A lot of online learning algorithms, actually the majority of online learning algorithms assume every time step you get a chunk of data, you get multiple data points. So it's very important to realize this is actually very harsh. Every time step you get only one data point. Once you move to the t+1, for example, all the information for time t and the previous one, they disappear. So they are not available to you to update the classifier. So the only information which is available to update the classifier is just one data point at a particular time step. Okay, so that's online learning. And this online learning algorithm runs forever. There's no separation between so-called training stage and the testing stage. And then you say, how do you apply this? So basically, the setup is at time t, you use the current classifier to make a prediction of intent output. Once the output is given, you use to control something or to do some classification, you move to time t+1. And then we assume that t+1, we know the true label of time t. So you have one data point for time t, which you can use to update the classifier, the t+1. In this particular case, data stream, if the data distribution is highly imbalanced, then there's a huge headache. Now let me explain why it's a huge headache. If I have a classifier which observes a data one at a time, then you can ask yourself, if I observe this class A, and I knew I observed some class B and C previously, how do I know this class A is minority or majority? You don't have one set where you can calculate 0.1, 0.2, 0.7 anymore. Then you say, oh, I can take a historical count, can't I? I can have a little counter to say class A, so far I have seen, say, 10 occurrences, and then class B, 3. I say, okay, you can use a counter and then remember the number of occurrences for different classes. Based on that, you can say which one is majority, which was minority. But things will change because the data stream, after some time period, this class imbalances ratio will change. You can imagine some of these minority classes might become majority. Some of the majority class might become minority. Then you can't have a fixed algorithm anymore because the majority and the minority is always time dependent. So we summarize in this online class imbalance learning. It's actually very few literature on this online class imbalance learning. It's a huge headache because answering the question whether this data stream currently is imbalanced or not can be a challenge. you say I'm going to remember counter. I did say this data stream goes forever. It's been like monitoring systems using sensors, and then you want to put some classifier into the sensors. You can't have a counter count infinitely, right? So in that case, how do you decide and balance this? So that's a challenge. Secondly, which class is minority, which class is majority? There's no fixed answer, it's time dependent. And then to calculate imbalance rate becomes less obvious. If a particular data set is very obvious, now it's less obvious. So this is really try to get to the bottom of the problem before we can develop any algorithms. So one set of very simple computational study we carried out a while ago is to use these online bagging algorithms. So this is actually a very popular algorithm, not developed by us, actually by other groups. It's very effective. If you're looking at online algorithms using ensembles, that would be my suggestion. Try bagging instead of boosting for online one. And then add some resampling method. And this resampling, it has to be a dynamic resampling because the class imbalance ratio is changing as the data comes in the data stream. So the particular investigation we did was to look at online bagging plus oversampling. Okay, and then the other one is online bagging, look at undersampling. That means according to the current situation, we guess which class is majority, which class is a minority, and then we always oversample the minority classes. Okay, we didn't touch the majority classes. For the alternative method is always undersample majority classes, don't touch any minority classes. And then we look at this two-class problem first, because multiple classes for online is too complicated to start with. And then this resampling rate is adjusted using a parameter. So there is a human decided parameter in this particular case. The advantage of having the second last bullet point is that once this parameter is set, adjust this resampling rate, we don't have to calculate this imbalance rate explicitly. The findings, so again, I skip all these detailed numbers. Very interesting is sampling in this case, because of two classes, is still very important. If you just use this popular online bagging, it won't perform as well as online bagging plus sampling, either oversampling or undersampling. In most cases, this undersampling has a better performance in terms of minority recall and G-means. So minority G-means geometric means considering multiple classes. Okay. The third point, again, is something a little bit unexpected before we see the result. Internal performance undersampling is good, but this oversampling is more robust against the imbalance rate changes. In online learning, people talk about online learning with the concept drift. Online learning with the concept drift basically means the underlying data distribution might change. But when you observe the data stream changes, how do you know it's just a stochastic change or underlying distribution has changed? So this is very important. For example, if you are in this photodiagnosis domain, you want to detect this concept drift because that means something has happened. The physical world has changed rather than just a stochastic sampling. In this case, this OOB, oversampling with online bagging, is more robust against these changes. Although when such a change did not happen, the performance of UOB is better. So it is desirable in practice if we are dealing with a data stream whose underlying distribution may change, then some kind of combination between UOB and OOB will be desirable. Otherwise, you might come up with a very good algorithm which is good at dealing with a stationary data stream, but not very good in dealing with the concentric. In that paper, there's a bit of a detailed description in terms of how to combine this OOB with UOB. And then the last thing I want to mention is actually very similar to what I described yesterday, is this multi-objective class imbalance learning is moving away from this classical machine learning thinking, because previous two steps, these are online class imbalance learning and multi-class imbalance learning, is very classical machine learning approaches. For this one, is more a combination between multi-objective evolutionary algorithms and class imbalance learning. Just a very quick comment before I mention this multi-objective class imbalance learning. The reason I didn't say too much about online class imbalance learning is really a problem which occurred in recent years. There are not a lot of references for the work I can present. So if you are interested in finding new problems to work on, that would be my suggestion. Online class imbalance learning. Normally you see people work on class imbalance learning or online learning, but both. Because mixing together, it just creates a headache for almost everyone. So very quickly as a review, in terms of multi-objective class imbalance learning, I mentioned that there are different ways in formulating class imbalance learning as a multi-objective. The first one, for those of you who were not here yesterday, is that if we have multiple classes, we can treat single class performance as a separate learning objective. If I have a 3-class problem, for example, I can have a 3-class learning problem. Okay, so this will avoid a situation where the majority class will overwhelm by multi-class. So it's a very nice way to separate the impact of majority class on a minority class. And then the challenge you bring with it is that now you introduce a 3-objective machine learning problem. What kind of algorithm are you going to use? Because all those popular tools, or TensorFlow, PyTorch, whatever, these are nice tools, will not be applicable anymore. And then the good news is that in evolutionary computation domain, there are a large set of multi-objective optimization algorithms we can actually take and apply to the machine learning domain. And the added advantage of using multi-objective evolutionary algorithms is they do not require these objective functions to be differentiable. You can actually put in non-differentiable loss functions as objective functions. So this is one formulation of class imbalance learning as a multi-objective learning method. The other formulation is to look at the learning goals. The goals of learning, if you use an ensemble approach, are very much as a high performance in mind. As an ensemble at the beginning, as I said, the second objective is we want to have a high diversity. Okay, so we can formulate this accuracy to represent this performance, and then we can formulate this diversity. These two as 2 separate objectives. We can add the third objective in terms of regularization. We can add the fourth objective in terms of energy saving. And as I said yesterday, how do you define the loss function for energy saving which is differentiable. It's extremely hard. In evolutionary approaches, you don't have to come up with a differentiable loss function. There's no need, of course, for sampling in this case if you have multi-objective approach. So this is just one slide add-on. If we are using ensemble approach, I mentioned yesterday, you can take the output from a multi-objective learning, test the ensemble directly. But sometimes you find the set of non-dominant solution to the set of learners you found through multi-objective learning is too large. Then you can always run so-called ensemble member selection algorithm to reduce the number of members within an ensemble. So this actually can be done quite easily using existing algorithms. Finally, some concluding remarks for class imbalance part. As I tried very hard to sell you this idea, even nowadays, these ensembles can be a very good idea. Even if you use deep models, using multiple deep models can still be a very good idea. And if you look at the literature, people do that. How to do that, of course, there are a bit of tricks. If you are interested in ensembles, then diversity is the key issue in ensemble learning. So if you're interested in ensemble to make ensemble to be more effective, then always start with diversity. And this diversity can occur in the loss functions you defined, error diversity. I also demonstrate this diversity can occur in the training data. So this is also very intuitive. Think of this, if I give huge amount of data, some data can be repetitive. It's not very useful, okay, intuitively. Some data are more useful because some data are more informative than others. The other way to think of this is data has some diversity. You don't want, with a quote, similar data to feed into the classifier because they don't really provide additional information. You want different data to feed into classifier. What do you mean different? You know, it's very easy for you to wave hands, but quantitatively, what do you mean? Actually, it is diversity. The concept can be used in terms of the data as well. Third point is if we gain a bit of insight into diversity role, normally we can design better algorithms. So in the previous 2 bullet points when I discussed this multi-class imbalance learning and online class imbalance learning, as a first step, I always try to understand this problem a little bit. I always try to understand the relationship between the diversity and the classifier performance a little bit. Because if I understand this relationship, I will be able to tune the norm in terms of diversity to influence outcome. So this is what I meant in terms of insight into diversity role. And the fourth one is really asking for opportunity to collaborate. If anyone's interested, I think this is a very good topic to work on. It has a lot of potential applications as well, especially if you think of some kind of monitoring system using sensors. Okay, so a lot of problems in those cases can be defined or can be formulated as an online class imbalance learning problem. If you send out these sensors distributed into some areas and then you want to monitor whether an engine or building has malfunction, for example, and then that problem can often be formulated as kind of online class imbalance learning problem. And the last one, as I said, half seriously, half in joke, we want people with more theoretical backgrounds to analyze the problem as well as the algorithm a bit. For all the results I present to you, they are based on computational studies. Certain data set using certain algorithms. instead of theoretical outcomes. I think theory is actually very important to make progress. So, so these are something else. So I stop here and take some questions. So it's an early finish for today.
Questions?
Yeah. Or comments, any suggestions? Yeah.
Let's say we have problems getting data for class content. Two of the classes then the class will be much data. So is there any insights on what one would expect as with regards to the reduction in performance as a majority class? Those two classes would be one would expect to be affected by this vaccine or what happened to the minority class?
Yeah, thank you very much for the question. So for this part of study, for this multi-class imbalanced learning, so there are two pieces of work. The first piece of work, indeed, we look at the two extremes. The one is a multi-minority scenario. The other one is a multi-majority scenario. The second piece of work, when we develop these algorithms, when we test this algorithm, one's AWS.NC, the other one is EYS. We did apply these two algorithms to different types of multi-class imbalanced learning problems. So within the data set we tested, there are cases you described. There are no obvious majority, no obvious minority. So we have a smaller classes, kind of medium classes, several in between, also one or two majority classes. Yeah. So in terms of final evaluation of the algorithm, we did contain these different types of distribution. But we have not gone into the details in terms of for each individual classes, especially those in the middle, how they perform with different parameters set up for the algorithm, for example.
Hello, and thank you for the presentation today. My question is, can you please explain again why in AdaBoost NC, having both misclassification and high diversity lead to larger weights is considered a good idea?
You were asking these slides, right? Were you asking about this last line? The weight updating rule of AdaBoost is
yes.
40. Yeah, okay.
Yes.
So what I was saying was traditionally AdaBoost emphasizes misclassification. So if you have a high classification error, it will lead to larger weight because we want to focus on misclassified samples when we reconstruct a training data set. So AWS.NC is a network correlation, introduced additional information into weighting. This additional information is this diversity. And this diversity is determined by the class imbalance ratio. So from the minority class, you get a larger weight. If you're from the majority class, you get a smaller weight. In the actual paper, there's a formula in terms of how these ambiguity term is calculated. But the principle which must be followed is minority class always attract larger weight. So I gave one example. If I have 3 classes, and then we have 10%, 20%, 70% in terms of class distribution, I can have a very simple class imbalance ratio of 0.1, 0.2, and 0.7. For the 0.1, it will attract the largest weight, and 0.2 the medium weight, and then 0.7 will have the smallest weight. This is a combination to the classification error. So it's only one modification to the traditional ADA boost is in the weight updating rule. Does that answer your question?
Yes, thank you. Thank you.
Thank you. Okay. Yeah. Yes. Okay. Let's start. Okay. So you can see here, this title is very different. It's an adventure for me as well. Lots of people ask me, this is a very woolly title, self-awareness and self-expression in computing. So this work I'm going to introduce is generated out of one European project a few years ago. And then I got into this area. I find it actually very interesting, especially in the current discussion about AI. And then I try to understand when people ask me about opinions in terms of weak AI, strong AI, super AI, hyper AI, whatever AI. I don't really understand that. And then I thought, if I have this opportunity, maybe I can share with you some of this previous work generated out of the EU project in terms of self-awareness and self-expression in computing. So feel free to disrupt me if you have any questions. So I spend a lot of time trying to explain where I'm coming from. Okay. So that's where I have this title, like, what does self-awareness mean? It's sort of my style of doing research. I really try to understand the particular terminology. If we are interested in self-aware and the self-expressive computing systems, what does it mean? What kind of system will be self-aware and self-expressive system? And then I use one case study to ground what I discussed before. And that example was actually a collaboration with a group of hardware people who are working on smart cameras. And then I look at one particular research problem in distributed smart cameras called the handover problem. It's kind of a very easy to describe problem. It can be quite interesting. And then I have some discussions in terms of what would be the other research issues related to self-awareness. So in the beginning, it might be very generic, very qualitative. I hope I can make something qualitative, slightly more quantitative. Otherwise, as engineers, it's very difficult to do anything. Self-awareness is actually not entirely new in computing literature. I think in some part of engineering, self-awareness has been mentioned quite a lot. people like this word, when they throw into this word into a paper and you carry on with discussion. But very few people seem to care what exactly it means. For example, you might have heard of autonomic computing, right, which is a term created by IBM. Watson researched that a while ago. Now nobody talk about it. But during the height of autonomic computing, self-awareness is one of the many keywords there. In Germany, there's a group of computer scientists working on organic computing. Obviously, lots of people using the term self-organizing systems, ubiquitous computing in communication. People always use self-aware communication systems. So this is a very, very good word for researchers to use. But what actually means? People just say, oh, it means self-aware. Okay, that's it. People don't seem to be very interested in precise description or definition of self-awareness. And then even people said that self-awareness is very important in computing systems. Computing in general, so mobile phone is a computing system, your watch is computing systems, all edge devices are computing systems. But if self-awareness is good, but how do we engineer a system which is self-aware? Very few people talk about it. If you want to put the concept into practice, I think we need to offer some guidelines in terms of engineering methodology. But this is not really in the literature. It's difficult to write a paper in terms of how to engineer self-aware computing system. Now, taking one step back, if I'm a computer engineer and then I'm given a task to design next generation of computing systems, then you can think, what will be the biggest challenge you will face? So here's my understanding in terms of characteristics of future environment this system will be in. So we'll be looking at a very large system. IT system will be large, like internet is IT system very large. It's going to be an open system. If you look at mobile communication, the base station can be added into the system anytime. It's not a closed system anymore. And a system is heterogeneous. It's just not an array of CPUs. It's not homogeneous, it's a heterogeneous or some very large node, like a supercomputer. That's a very small node, like a mobile phone, so it's a heterogeneous. And then the system is always operating in an uncertain dynamic environment. You cannot assume the environment is fixed. The system itself is uncertain dynamic. So the mobile phone always has a probability with non-zero to fail. If I connect this mobile phone into a network, you have to consider the probability of failure. Okay? If you have a millionth mobile phone connected to a network, and then you have to worry about the potential impact of uncertainty on my system. Decentralization is also a very important characteristic of future IT systems. So distributed systems might not be decentralized because distributed systems can have a master-slave structure. So you have still have master. Fully decentralized system, there's no masters. How do you ensure such a system can behave and display some global behaviors while you don't have a central control? Interesting questions, right? When we build this next generation of computing systems, there will be lots of requirements, not just single one. Performance, of course, will be there. Every system built, people say it needs to be high performance. But then you have other requirements like flexibility. I want a flexible system. I want system to use the least amount of resources, energy consumption, for example, occupied spaces, for example. I want system to be secure. I want system to be reliable. So you have a lot of what I call non-functional properties, which are becoming very important. Non-functional, that means the system will function, but the security is terrible, or the resource consumption is terrible. In olden days, that might be tolerated. You put it into a computer center, but in the future, that will be less tolerated. There's a high demand in terms of energy saving, in terms of higher security, etc. If you look at all these different goals, a lot of them are conflicting with each other. If you want something highly reliable, high performance, normally you consume more resources. There's no free lunch in this world. If you have something about high quality, it's going to cost you. So when we look at these goals and the requirements, it's not going to be one fixed number anymore. So if you look at the output for computing system, you measure it into the flops, for example, it's not a fixed number. It's going to be a time-dependent behavior. So that's how we evaluate the system. The key challenge, I claim, this is a claim, I think something for discussion. We should move away from designing the optimal or the best system. I think the optimal and the best, these two words need to be questioned, because if you consider the scenario for the future computing systems, if you look at the multiple requirements who are conflicting with each other, that best or the optimal is extremely hard to define. So the key challenge from now on, I claim, we should all think of how do we design a system, whether a computing system or communication system, which can dynamically manage trade-offs among different goals at the right time. So a lot of keywords here. It's not optimal system we are designing. We are managing trade-offs. Why? Because these goals, they are conflicting with each other. We want high performance. You want to get performance GPT-4, but you don't want to spend the electricity bill of GPT-4. Okay, you have to come up with a trade-off. Okay, a keyword. Now, this trade-off is not a fixed. It's time-dependent. So this trade-off needs to be managed dynamically. So it's keyword. And then it has to be managed at the right time. So we have to move away from the concept we are engineers, we design product, and then we deploy the product, then bye-bye. We have a design time, we have a run time in the traditional thinking of engineer. But I claim that the boundary between design time and run time will be blurred. A lot of management work, this managed work, will be at the run time. That'll be the future for these computing systems. Okay, after projecting, these are major challenge in developing new computing systems in the future environment. So what do we do? What is our starting point if we are going to design a new computing system? Firstly, as I mentioned, I want to design a system with an acceptable trade-off among multiple goals. So the word is acceptable, not optimal system, not the best system. Okay, because optimal and best, I think that word can be misleading. And secondly, in design time, we already consider deploy environment. And that deploy environment comprising of dynamic and uncertain scenarios. So if we design any engineering system or computing systems, we have to consider when the system is deployed, that environment has some inherent uncertainty. And then we need to build in, we need to enable a system with the capability of dealing with uncertainty. So it's not just a one-time optimization, as I mentioned previously, either this morning or yesterday. So the overall gain is really the dynamically managed trade-offs at the runtime. Okay, how do we do all this overall gain? In order to ground this, to get something more concrete, we make some assumptions. Okay, so here assumption comes into it, and then we can actually test these assumptions to see whether they hold or not. The first one is in the future, when we build a system, doesn't really matter as computing, communication, or engineering system. If the system is aware of its own states, its own behavior, its performance, then such a system can manage the trade-offs I mentioned better than other systems which are not aware of this. They say, how can you make this claim? Well, this is my hypothesis, my starting point. Systems which are aware of its own state, own behavior, and own performance can perform better. This awareness will enable them to better meet this conflicting requirement. This is my hypothesis. Now, the design approach I'm going to use is for all the systems I'm going to design, I imagine this system is a collection of self-aware, self-expressive nodes. These nodes are computational nodes, which can learn, can interact, and can self-adapt and self-organize. Now the question comes into it, starting point for research. You make this hypothesis, and then you design a system as a collection of computational nodes. Are there any benefits of doing this? Or where are these benefits? Or when these are beneficial to do this? Okay, the first question. Second question is, how do we do it? Okay, if you said this, being aware of their own state, behavior, and performance is good. How do we do it? Assuming it's good. Okay, so that's two research questions. So we want to decompose into more detailed research questions. So this is the European project I participated a few years ago. The project is called EPICS. So the overall approach is we kind of believe this self-awareness and self-expression is useful for computing systems in the starting point. So what do we do as an overall research approach? We obviously need to learn from psychologists and cognitive scientists what they define as being self-aware. Okay? And then we look at the current computing systems to come up with a working definition. So this working definition will be more specific, will be a guideline for doing engineering work. So this arrow is a bit like we try to translate what's discovered by cognitive scientists into the engineering domain. And then in order to demonstrate whether this working definition actually is appropriate, there are two parallel lines. One is to define how do you evaluate this working definition. The other one is actually come up with the reference architecture for future computing systems. Fairly ambitious goal. And then finally, as most EU projects, you need to have a demonstrator. So this is actually a set of demonstrators. You can see there's a distributed smart camera network. I'm going to say something, only a small part of it. And the second demonstrator is a virtual hyper music. It's quite interesting. It's very interactive. The third one is a self-aware SOA, service level agreement management in the cloud computing. The fourth one is a task scheduling for heterogeneous clusters, computing clusters. And the last one is a scenario-based evaluation for pro-receptive architectures. Always have trouble pronouncing that word. So that's the overall background of this. And then the research objective is really to provide systematic understanding of self-awareness. I'm going to explain that a little bit. The second one is very important for engineers to establish a methodology for engineering such a system. So as one of the outcomes for that project, we actually have edited one book. is called the self-aware computing system, but subtitle, it is called the engineering approach, emphasize the engineering aspect of it. So these okay. So this is the part which we learn from psychology and cognitive science. To me, it's very interesting. Okay, I want to share this part with you. There are two different ways in which a person can be self-aware. This is what I learned from psychologists. Very interesting. First one is called private self-awareness. What it means as a person, the knowledge about yourself is a part of private self-awareness. And then your internal state is part of your self-awareness. It's been like, I'm hungry. This is added by me, okay? Psychologists never say that. My battery level is low. I added it for me, and I say, okay, these are psychologists. What do you mean for a computer scientist or computer engineer? I say, or maybe if a computing system, that system knows its battery level, maybe that's the internal state. And this self-awareness is externally unobservable. So what I'm thinking internally, you won't be able to see. It's internal to myself. This awareness also includes values or goals. If I'm persistent, I might have some goals or value I want to pursue. This value and the goal can be anything. It can be some kind of performance goal I have. Can be a goal saying I want to stay alive. That means if I'm a sort of a sensor running on a battery, one of my goals is to survive as long as possible. Okay, I can put my performance as a secondary goal. So that's how I understand this psychological view of a private self-awareness. So it's everything about me. Do I know what I know? So this is self-awareness. The second self-awareness, also about the person. Okay, this is not public. It is called a public self-awareness about me. It's aware how others see me. So I'm aware how Mario perceives me, how Christus perceives me. So if I do have this knowledge, then I have this public self-awareness. Then I always try to connect to a computer system. What does it mean? Oh, it probably means in a network, if I'm one node, I know the capability of other nodes. I know how other nodes will see me in terms of my CPU power, in terms of my bandwidth, etc. Okay, that's how I make a link mentally. Also aware of relationship to others. So what kind of communication I can have with you, or what other kind of communication I can have with you, which can be type of message I'm passing in terms of bandwidth available, etc. So awareness of relationship. Also reflective. That means I can observe the interaction and then I can make reasoning. Okay. This public self-awareness also requires knowledge of the environment of the others. So if I deploy the system, not only I have some knowledge about my neighboring nodes, I also have some awareness of the environment. Anything about environment. Okay. So these are the two types of self-aware. So whenever from now on I said that I'm self-aware or particular mobile phone device is self-aware, there are two types of meaning there. And this mobile phone knows it is of internal state, it also knows which other devices it's connecting to, and also is aware what other devices will perceive particular mobile phone here. So that's one input from psychology. The other one is also very interesting. I think I learned quite a lot from these levels of self-awareness from psychologists. The simplest one, you could imagine it as the lowest one, is called ecological self. So this term is actually borrowed from psychology. So it describes the very basic stimulus response system. If you give stimulus, it's a response. Stimulus response. So in psychology, they say the absence of unconsciousness is called the ecological self. And so this stimulus response system is sort of my interpretation into it. It's much easier for engineer to understand it. The second one is getting slightly more interesting. It's called the interpersonal self. It's self-aware. It's a very simple awareness of interaction with others, allow simple adaptive working. The third one is called the extended self. So the red part is added by me, and then the blue part is original term. I try to understand the essence of it. So extended self means ability in terms of reflecting over time. So sometimes when I discuss with a colleague and I say, if you don't like these psychological terms, interpersonal self, extended self, maybe you can use my understanding. My understanding is interpersonal self describing one system which can interact spatially. So there's a bit of awareness in terms of spatial relationship. And then in terms of third, extended self, you can understand this self-awareness includes time element, time aware, aware the history of interaction with other nodes or with the environment, or within myself as well. The fourth one is called private self. Is also one type of self-awareness according to psychologists. That means that if you have self-information, that means that if you have internal thoughts, if you have feelings, if you have intentions. These intentions, I use a red one, is added by me. The reason I did not think of too much about the thoughts and the feelings, because I find it quite difficult to map to an engineering system. But this intention could potentially be mapped into engineering system. If you have one computational node like mobile phone, you can always think, oh, if the self-aware, does this mobile phone generate its own goals instead of externally imposing the goal to it? And that's interesting, right? So this private self describing the self-awareness whether the system can generate its own goals. I use an imprecise example to illustrate this example. If I have a mobile phone I want to use, but this mobile phone is self-aware, its battery is running very low. When I try to use this navigator, which consumes a lot of battery, if it's self-aware, it will refuse my request and say, no, I'm not going to run this because I don't have the battery to run. Okay, so that's how I understand the importance of this private self. The fifth one is called self-concept. It's self-awareness, whether this system has the ability to do abstraction, abstract symbolic representation of oneself. The reason I find it interesting is if you compare this old work by psychologists with the modern discussion of weak versus strong AI, I think this is more interesting, personally. Okay? I think it captures more like these woolly words of strong AI. I still don't know exactly what it means to be strong AI. And this actually gives me kind of a different way in understand what the future system should have. System should be able to be aware, spatially, temporally, like this second and third one. The system should be able to generate its own goals. Otherwise, how can you call a system as an autonomous system? If you have an autonomous system, that means the system can actually decide its own goals. Okay, so this is more like a private self. It might have some feelings. I can't find an example in engineering terms what the feelings or thoughts are. But internal thoughts, it might be analogous to an internal model which can do the reasoning for autonomous system. And then in terms of self-concept, very few systems can do nowadays because we make observation. All the current AI systems are very good at the perception tasks, either in terms of vision, in terms of speech, in terms of language. But in terms of abstraction, I think it's still struggling. Okay? How do you convert this perception into abstract symbolic representation? It's very interesting one. We can go on because there are psychologists said in addition to the first 5 levels, there's one level called meta self-awareness, which means, are you aware you are self-aware? When you say, are you playing the words? No, not playing the words. Be aware you are self-aware. So I'd say it's a little bit like the parents told me, you need to be aware your own capability, what you can do. Tiny bit of similar to that. So being aware, one's self-aware is very important. It's a bit like knowing your limit. Knowing your limit, obviously, is very relevant in building engineering systems. If you develop an autonomous system, autonomous driving, for example, you want to ensure this vehicle is not going to harm human beings. It's not going to run into buildings, stay on the road. How do you ensure that? If you just look at billions and billions of pictures, how do you do it? Okay, obviously, it's a very interesting question. Okay. And then if you go through this even further, there's another type of self-awareness might be more relevant in a fully decentralized system. It's called the emergence of self-awareness. So the key point for this emergence of self-awareness, if you look at complex systems, at the system level, you can see, oh, this behavior appears to have some self-awareness, okay, as I described previously. But if you look at it as a component, you don't make that observation. But this is different from all the previous types. You can observe self-awareness behavior at the system level, but at the component level, you don't observe. So you can think of some examples of that. If you look at examples of social insects, for example, if you look at the individual insect like ant, you say, well, it's not very clever. It doesn't really have so-called intelligent behaviors. But if you look at the entire colony, you say, oh, well, that's quite smart in terms of finding the shortest route in terms of decision making. Similarly, if you look at other social insects like bees, one single bee observed is not really smart. No matter how you look at it, it's just a bee. But if you look at one hive of bees, you can say, geez, that's very smart. The way they built their hives, it's very smart. Okay, in terms of maintaining the temperature where they are staying. So this emergence of self-awareness in my understanding is trying to capture that element. For the whole system, self-aware, but for the component, you don't make that observation. So if you are interested in what I mentioned in this introduction, and then you can find some literature in the psychology domain looking at the public versus private self-awareness, level of self-awareness, emergence of self-awareness. If you are interested in finding out how far people have gone in taking this concept into engineering domain, so those are the 5 domains we can identify in computing. If you look at the literature of autonomic or organic computing, they talk about self-awareness. If you look at the literature in terms of metacognition, and they talk about self-awareness. And then engineering self-awareness systems, self-awareness in pervasive computing system with emergent self-awareness. So all those keywords you can type in Google, they will return a few publications related to that. So that's a kind of a longer introduction, try to answer what does self-awareness mean. It actually means quite a lot, according to studies from psychology. Now we want to take a smaller step forward, say, okay, that's what the psychologists do. But for a computing system to be self-aware, what does it mean? Now, we have to come up with this definition ourselves, no such definition. So we call the definition we are trying to come up with as a working definition. And this working definition is because if I don't put the word working, people always ask me this definition is incomplete, imprecise, it has not captured certain elements in psychology. So working definition has a sense that I want to come up with a definition which enable my engineering research to go forward. So I know this definition is incomplete, but it's sufficient for me to move forward. That's why I use a word as a working definition. An assumption made is we are looking at a system. This system consists of a number of computational nodes. So then you say, what's the example? One example could be internet, would be such a system. If you're looking at a network of base stations in mobile communication, would be such a system. So it's an open, fully decentralized system where there are a number of nodes. In internet, each node is just one computer. In a mobile communication network, each node will be a base station. But this computational node can also be a person if you're thinking about a network with a mixture of computing devices and people. Okay, so computational node basically defines a kind of an abstract notion where some agency exists. You can do the information processing. It can be very small, can be a watch, or can be just a sensor. It can be very big, like a supercomputer. Okay, so that's first assumption. For the system I built, it is a number of computational nodes, and then they're connected in certain topology together. Nodes is really represent level of abstraction. So a system consists of one or more. For those systems which is not consists of computational nodes, then it's not in my consideration. There it goes. So that's how I define from an engineering perspective. If I'm looking at computational nodes, piece of software, piece of hardware, etc. To be self-aware, this node must possess both private and public self-awareness. Okay, this node is of internal state. It also has knowledge about the environment. So if you design a computational node, it can be hardware or software system. To be self-aware, if you want to enable self-awareness to this node must possess knowledge about its internal state and knowledge about its environment. Its environment consists of other neighboring nodes as well as physical environment. Optionally, when we design this as a self-aware node, it can also possess knowledge about its role or importance within the wider system. So whether this may be, if you look at the system, there might be some terminals, there might be some relays. So the relay is aware, it's a relay. Okay, so this is what it says. It can also possess knowledge about the likely effects of potential future actions, decisions. So as a relay, that means I take some information from the terminals and pass on to the next stage. So that knowledge can be embedded into this particular node. It can also have a historical knowledge in terms of interactions. And then it might have a capability in deciding what is or is not relevant. Okay. All this can be part of self-aware node. If you want to see this self-aware node, that's the diagram we have shown. Now this is somewhat closer to my engineering interest now. If you want to design a system, you say this system is self-aware. They say, what do you mean? And I say, well, if you want system to be self-aware, I think you need these three components in your system. Okay? There's a private self-awareness engine, which is trying to sense the internal state of yourself. I gave some example. You can sense the battery level, you can sense your CPU power, you can sense the bandwidth, you can sense any sort of reliability of the system, for example. But it's all internal. So these sensors here, they are all internal sensors, like sensing the battery level, sensing the bandwidth, etc. Okay. Externally, you won't be able to see. In addition to that, there's also a public self-awareness engine where you have the knowledge about other nodes connecting to you. For nodes not connecting to you, of course, you don't know. You also have some information from the environment. Because of this self-awareness in terms of private and public, this self-aware node normally have an internal model. There's a lot of self-awareness comes from this model. So this model is built based on the state and the context, the state including internal state, external state. So this is my working definition in terms of what self-awareness node should have. If you have this, it can be hardware as well. Yes, yes. So these are nodes. So this node is really just levels of abstraction. So if you said in my representation, I don't want this mobile phone to be a node, I can define all the devices connecting to myself, including my watch, as one node. So it's really a level of abstraction where you want. So in that case, it does contain the actual hardware, including me as a person, as well as the software embedded in the watch, in the glasses, in the mobile phone.
And the model, is it a model of itself or a model of the environment?
It's actually both. So this model, this learned model, we put a bracket with S, as an internal model because it tries to understand itself. And then it also tries to understand its position within this environment, in terms of physical environment, and connecting to other nodes. So I mentioned connecting to other nodes, there are a number of different things which can be sensed through these models. Okay, so this is very important. If you don't have an internal model, I don't think you can get a higher level of self-awareness. If you don't have an internal model, then it's really like a stimulus response system, give an input and response. It's very difficult for you to reason spatially or temporally. If everything is internal model, you can imagine these levels of self-awareness I mentioned could potentially be implemented. It's very important to have internal model. Okay, so this is a quite important step in my talk. So how we come up with this self-aware node architecture, you can call it this architecture name. You can do some engineering work out of this, either in terms of software implementation or hardware implementation. In terms of self-expression, it's slightly easier. If you're aware, then you need to take actions. So that's how we see the relationship between self-awareness and self-expression. So self-awareness, in my introduction, you can see, it concerns about a system of knowledge about self. And then the self expression really about actions. If you are aware about yourself, what actions you are going to take. Keep in mind, these actions can be on myself. Then I change my internal state. But this action can also be on other nodes, sending information, receiving information. This action can also be on a physical environment. If you have, I don't know, autonomous cars, so you into a physical environment. So that's how we see self-expression is really about action. The working definition of a self-expressive node is it's able to assert its behavior upon either itself, as I said, or other nodes, or both. How do you make this action? You can imagine now this action is based on the node's internal state, context, including physical environment, its goals, its values, objectives, constraints. So that's how these actions were expressed. So if you see in terms of diagram, it's a bit like that. There is one self-expressive engine, generating actions. It takes this state and the context is coming from sort of a self-aware node. Also, is determined by the internal goals, values, objective constraints. And then the action, the actuator can be operated internally. That's why within the big box, it can be externally. And the final one, it's a bit like for this part, this concluding slide is if I have one computational node, which is both self-aware and the self-expressive, we call it the proprioceptive node, combining this self-awareness part with the self-expression part. The only new component put it in is this meta self-awareness as some kind of monitor and a controller. Some people ask me, well, what are these? Well, these are being aware you are self-aware. I say, was it useful? As an engineer asked, was it useful? To me, I believe this is potentially useful, maybe in an autonomous system, because when you develop autonomous system, you always look at the historical information. You can't really predict the future. But you want to ensure in the future, if you will not do something bad, with bad to be defined. Not the meta self-awareness, it can act as a controller. If I know yourself, if I know I'm self-aware, I know your capability. So there's a potential I can set limit to it. So that's how I see the potential use of meta self-awareness. I haven't developed any system on that yet, but that's how I see the importance of meta self-awareness here. So this is actually a summary to say this proprioceptive computing system is really says it's both self-aware and self-expressive. It's comprised of one or more receptive nodes, which is very similar. The nodes are connected in sound topology, and they interact with each other through self-expressive behaviors and public self-awareness. Okay, so those 2 points are very, very conceptual. Okay, the first one, self-awareness, I introduced from psychologist's point of view. And then the third bullet point here, I try to ground it or bring it closer to engineering. Now I want to make an effort to make it slightly more concrete through an example. Although this example might not be ideal, but this is the work we did through a project. I will use it. Let me first describe a rather generic scenario to you, so you can see, although I'm describing one case study, probably I'm describing a class of case studies. So maybe you have an engineering scenario where you have a decentralized system. So this smart camera system will be decentralized system. I can outline the background is if you want to have a camera system deployed in airport, for example, distributed in various places at the airport, and then you want to track objects, track me, because I'm a suspect. What's this Chinese tall guy? You know, he looks very suspicious in Cyprus. So tracking an object in this fully decentralized system is not easy because you have multiple cameras. One camera track me, and then I'm moving. Then I'm going out of view. Then somehow you have to tell some other cameras, please, you check that person. Then there's a handover issue. How do you know the other camera, and then such that you can hand this object to the camera? Okay, so that's one scenario. But more generic scenario I'll describe first, and then move on to that. Or maybe I describe that directly. If you have a question, I can come back to this generic one, since I already described in these examples now. In this case, I believe current implementation for all airport systems is that you have a central control room. Okay, you control huge monitor. And then in that control room, you know exactly where each camera is. You know exactly the capability of each camera, right? So in advance, you know if a camera A is checking an object, if a passing out of the view of camera A, it should be handed over to camera C, for example. Because the whole system is designed by me, I put it there, and then I have a central control there. No problem, everybody using it, or still using it. But the problem is, what if some camera failed? Then you want to hand over this object to camera C. Camera C is failed. Then you lost this person, right? Then I want you to imagine a future camera system at the airport where the cameras can be added to the network or removed from network at any time. So the system is fully decentralized. It's very good. So I can have a mobile camera moving. Then how do you do handover in this case? Because you don't actually know what the next camera will be to you now. Right? Secondly, I assume in the future, you have so many cameras, at least one or two will fail. You don't know which one will fail. You want to make sure you don't hand over the object to a failed camera. So this is called the handover problem. This vision graph basically describes whether you can have this topological structure to tell you which camera is closest to which other camera. Because if you know this information, handover will be trivial. You pass on to the nearest camera. Okay. We are looking at this fully decentralized open camera network. We will not have this vision graph in advance because we don't know the structure. So using this scenario I explained, I'm going to describe a very simple scheme. This scheme, partially based on end-based mechanism, is not end quality optimization, nothing to do with optimization. And then I'm going to explain how we can grow this vision graph during runtime. Okay? I don't need to know the structure in advance. And then I don't even need to know the topological information where cameras are in advance either. Okay? And then I claim what I'm going to describe is very scalable, is very robust to camera failure. How do you do that? Okay. So this is a scenario I'm looking at And then to describe what I said, suppose all these green dots are the cameras. Each camera will have a field of view like this triangle. So in the simplest case, in scenario 1, I have one black dot moving from left to right. And then if I look at this picture, I know if this is the camera, if this red dot is moving towards right, this red dot should be handed over by the green one to the next screen. But if you don't know this, they sort of lost. So the scheme is like the following, if I go to this. If I'm tracking an object as a camera, and I sense this object is moving, is going to leave my field of view, step number 1, I'm going to host an auction. I'm going to host an auction. Okay, so this is borrowing some ideas from economics. Basically said, I have one object for sale. Okay. And then I can broadcast this message. And then all the other cameras, the smart camera, they receive this message. They will bid for this object. Me. I will keep tracking this object. But this bidding, it depends on your own capability because I'm looking at the heterogeneous cameras. Some cameras are more powerful than other cameras. So if you sense stronger signal, that means you are physically closer to this auction, then you can bid for more. If you are aware you have a stronger capability, so a more powerful CPU, higher bandwidth, you can bid for. Okay, so we host this auction. And then this camera hosting the auction will receive all the bids and then pass on this object to the successful bidder. And that's how the handover is solved. You see, in this process I described in words, I don't need to know where the camera physically is because I receive this message. I pay a price, of course, because broadcasting consumes my energy. Then you worry, so what if I broadcast the signal, some camera don't receive it? Then it's good, because if you don't receive this message, that means either you are physically very far away from me, or your capability is too weak to take over this tracking task. I want to sort of get rid of you in the first place. Okay, so this is actually passing on. Now there are some details. What kind of auction mechanism do we use? So this is actually not invented by us. So we look at this multi-agent domain. They use this auction-based mechanism quite a lot. In implementation, we use some kind of weekly auction. It's actually often used in Dutch. Everyone bid with a particular price, but we give the bid to the highest bidder, but the price is the second highest price. So you award the item, the object to be tracked to the highest bidder, at the price bid by the second highest bidder. They probably say, okay, I know this is a detail, but I'm still interested in this detail. Why do you use this? The reason we use this particular one is when we look at the literature, they said, if you use this weekly auction, people will have to bid for their truthful valuation. So that's from otherwise, it's not going to have a dominant strategy for bidding. Highest bidders is the bidder with the highest price, artificial price. No, the price, you use the second highest bidder. So suppose Mario bid for 10 euros, you bid for 9 euros. So Mario will win the bid, but Mario only need to pay 9 euros, not 10 euros a bid. So he's still the winner, but he don't actually pay 10 euros. He can actually pay 9 euros. So that's so the reason for the detail we use this one is because it encourages people to be truthfully evaluate itself in terms of what's your capability in terms of checking the object, what's the strength of signal you perceived. Talking about the bidding, I say, how do you this awareness comes from? For each computational node, we defined a utility function. I keep talking about the computational node needs to be aware its value, its goal, this kind of value of the goal. It describes, so all these are using sort of economic terms, but it really try to describe what kind of benefits you can receive by tracking the object, because when you define this utility function, this is actually by human beings. So as a designer, you define utility function. You need to incentivize all these cameras to track objects. The more objects tracked, the higher the value. However, there's a cost. The cost is dependent on this price and then this reward. So there's a bit of a balance there. You can't just beat the arbitrary sort of something, but with a very low confidence in yourself. Confidence related to your capability. So this part is manually designed. That's why you can have this auction mechanism. So that's one detail. The second detail is I said I don't need to know the architecture of the smart camera network in the beginning, and then I want to build up this vision graph. So the vision graph, you can imagine it's a bit like a logical topology of cameras. It's not physical distance, because if I'm very close to a camera, but that camera is very weak, but there's another camera further away in physical distance, but it's very strong. So that very strong one can be my neighbor instead of the weak one. Okay. So the vision graph is looking at the capability as well as the distance. So what you can do is, let me switch. I should have one. Let me find slide in building. This one. So this actually, I want to use this slide to illustrate how online vision graph was built. So this is one simulation we did. This is a snapshot. So this is iteration 0. All this green dot is actually lighter colored dot is a camera. All these black dots are the objects. So it's actually not tracking one object, it's tracking multiple objects. And then all these cameras are facing this cross line, more like a rose. So field of view towards them. And then this iteration 100 means we have this auction hold, and then we move the object from one camera to the other camera. We define that for one trade option successful. Right? Whenever there's one trade, we make a link between this camera to the other successful camera. So if you look at the color and the width of the line in this particular diagram, if you represent between two cameras how many times there have been trades. The darker color, the more red the color, the thicker the color, that means there are more trades between these two cameras. Okay. So this is what it means. So this is a lighter one. And then as out of iteration 300, you can actually see this kind of vision graph. So vision graph, all this red color, very thick line means that there are a lot of trading between these two cameras in terms of passing object from one camera to the other. This actually indicates logically, these two cameras are very close to each other. You've got to keep trading, considering both their capabilities and physical distance. Then you say, well, okay, what's the use of building this vision graph? It's very useful because for all of us with a communication background knows broadcasting spam not only consume energy, you also flood the system with so many messages, especially if you are checking multiple objects. Once you have this vision graph, you know who your neighbors are. So next time, iteratively, you don't do broadcasting anymore. You only pass auction signal to your neighbors. Then you say, where's your neighbors? Well, the neighbors is defined by your vision graph. Okay, so that's why the whole system is adaptive. You build a vision graph, you use vision graph to define your neighboring cameras. And then next time when you hold auction, try to pass a tracking object, you only pass a signal to the neighboring cameras, and neighboring cameras will return the bidding. And then you keep going. So there are other details. Maybe this bit of detail will also be useful. This where this ant-inspired comes into it. It's a pheromone-based vision graph generation. So this slide is to answer the question, okay, if you have a lot of trading between two cameras, okay, and that doesn't mean the strength between these two cameras will only go up, will never go down. The answer is no. If within a time period, there are no trades between two cameras, so the strength of the link will be weakened. How do you weaken it? Well, we use an analogy of this pheromone. So every time when you have a trade, it's a bit like an ant leave a pheromone. But this pheromone will have a degrading or decreasing strength. Unless you keep trading, this link will be weaker and weaker. If you never trade again after trading some period, and then this link will disappear. That means in the online vision graph, there's no such link anymore. Okay? So this is a pheromone update. In terms of detail, the formula I can explain later on, but it's not very interesting. Yeah. But this idea in terms of you can strengthen the link and then you can weaken the link is actually quite important. And then you can come up with a different communication strategies to look at the trade-off between the cost of communication and the optimality in terms of utility. And this one is used to illustrate there is always a trade-off between different goals. Okay? If you look at the x-axis here, it indicates a communication overhead, whether you are likely to flood the system or not. Larger one is actually bad if you flood the system. And the y-axis here, in terms of total utility, you want the utility to be as high as possible. You want the communication cost to be as low as possible. Then you can see there is some kind of Pareto front here. That's why at the very beginning I said that when you design these systems, we are looking at the trade-off. There's nothing optimal. If this is optimal for the other objective, then it's not optimal anymore. I think this is another thing I want to say. Yeah. Now, without boring you with all the detail, you can imagine for my verbally describe the algorithm, it doesn't really matter how many cameras you have, right? It's a fully decentralized system. It's based on the camera which has the object. So now you can do a mental exercise. If you have a smart camera network, you suddenly add in 10 cameras. The algorithm does not change a single bit because when I have an object, I still do the broadcasting. If you're adding more cameras, for those cameras can receive message or just participate in it, I don't need to change my algorithm. And every single camera can run exactly the same algorithm. If you say, I have built up this vision graph here, then you say, well, what if this camera suddenly failed? What happens? It will take amount of time, a few iterations to recover, because next time when one of the camera is hosting a bit, this camera will not participate in a bit because it failed. It will never participate in a bit. Because of the pheromone update scheme I just mentioned, all the links to this failed camera will gradually disappear. So you can see this vision graph will adapt to the failure of the camera. That's why I put in one slide to emphasize this algorithm is very robust because you can add in cameras anytime, you can move camera anywhere you want. You don't need to change the algorithm. It's a fully decentralized algorithm. And the scalability is very good because you only look at the local auction. Whoever who can receive by auction signal participated in it. For others, it doesn't really matter. So you can have a huge network, it's okay, the algorithm still works. So this is actually the case study I present. In general, coming back to, you can think of some other systems which have similarities to what I described in the smart networks, smart cameras. Maybe you can have smart sensor networks for monitoring weather, whatever. Okay. So that would be very similar scenario where you can use a market mechanism in terms of communication. You can build up a conceptual or logical structure in terms of topology. Okay. And this topology will evolve according to the changes in the environment. And then it's robust against the failures of some sensors. And then it's robust in terms of its scalability will be much better than other centralized systems. It's a link to this self-awareness, this particular map I put it in. So how do you think? You can see this particular utility function is kind of private information because a node, I define utility function. I'm not disclosing this utility function in other nodes. It's unnecessary anyway. And public self-awareness is really in terms of communication with others. In this case, it's really bidding activities. Okay. Self-expression is really the communication strategies. If you know the bidding information, if you know your internal evaluation, what kind of action would take. So this is actually in terms of self-expression part. There is a meta self-awareness I didn't explain in my slide. It's more detailed, which is very specific to a smart camera networks. So that's actually all I want to describe about this particular example. So related issue, that a bit is very specific, I skipped. So this part I describe in words, but there are actually computational study you can do, try to observe whether you get into undesirable critical values, because one of the major results from this study is for x-axis, you can say the number of cameras fails. Y-axis is system performance. System performance is measured in terms of number of objects you fail to check. And then we want to observe whether there's a critical value in terms of number of camera fails where the whole system collapses. And the answer is no. You observe what we call graceful degradation of the system, which is very good for all engineering systems. The other part, which is a completely different story, instead of looking at the smart camera network, you can look at federated clouds. It's very much in computer science domain. We can apply exactly the same thinking of the design principle to this. Lastly, I did promise you, if you have one application you are interested in, or you are interested to ask your student to do it, and then you still ask me, say, how? I need the starting point. So we actually wrote a 70 or 80 pages handbook asking, said, if you are really interested in designing a software and software system, what you do step by step. It's not really publishable as a scientific paper, but as a practical guide, it's quite useful, especially if you want to build an engineering system. If you have undergraduate students, for example, who are interested, we put this simulator, so the simulator generating all this vision graph online. I hope it's still there. One of the students in Austria, I think, built a master thesis around this particular casing. I think he has improved quite substantially. So by all means, you can just use it, play around yourself, and then try to answer some research questions you find interesting. So finally, the conclusion is just a few messages. First one is a claim. They can be debatable. So my claim is at the design time, if we explicitly consider self-awareness and self-expression, we can design better systems. I want to encourage people to have this explicit consideration in terms of self-awareness at the design time. Of course, the only evidence I present today is just a distributed or fully decentralized smart camera networks, but there are actually other examples. If we explicitly consider self-awareness, we are able to manage trade-offs between conflicting goals at the runtime better than not using this approach. You can use other approach, but might not be as good as this one. Secondly, in terms of goals we are interested in, we need to include adaptivity, especially as I mentioned, if I'm interested in vision graph, and I want to make sure this vision graph will change as the environment changes. So I can have one particular link being strengthened, a particular link being weakened, depending on current situation. And then in the smart camera network, actually, we only look at the two goals. One is performance, the other one is communication overhead. But there are a lot more other things, security, reliability, to be considered in other systems as well. The last one is really try to claim that we start with these qualitative psychological concepts, and then we try very hard to turn those concepts into something which we can use as a guide in engineering applications. So finally, a lot of people make comments. That's actually last line was a reviewer's comment when we sent this paper to ACM. So when we send these papers to these two ACM transactions, in both cases, there's at least one reviewer said, you are making too many simplifications for smart camera handover. Is that in reality, it's far more complex than that. Because we assume that all the other cameras can actually see the object, he said that might not be the case. Because you need to be able to see the object, Then you can evaluate whether you have a capability to check it. He said, well, in some cases, you won't be able to see it in the first place. So I put this comment here saying, if you really want to have a real-world application, there are still some gaps. I will stop here. Thank you very much for your attention. So this is a bit far away from evolutionary organization. But I find it interesting. So. Yes.
It's user.
So your question is, how does this camera know to check this object? So how was being told by someone? So this is actually in a utility function defined by human beings. So yeah, so when we design this node, we define the utility function. We tell them that if you want to minimize, or you want to maximize your utility, you need to check objects. The more objects you check, and then the higher your utility. The specific object, yeah. We tell them to check specific object. So this part is actually designed, as I said, this utility function is designed by human beings. And then for all the cameras, we tell them, you need to maximize your utility. Well, they always want to maximize utility. And then we tell them, in order to maximize utility, you need to check as many objects as possible. And then we tell them which object, or what types of objects to check. But the goal is unclear because it costs you to check objects. When you take a bid, you need to take money. Right? So there's a minus term in your utility. If you don't have a very good tracking performance, and then you have to pay 10 euros, for example, it's better not to check it, actually. Otherwise, your utility will be low. And this is also relative, depends on how others are bidding. So it is kind of optimization, but you do have multiple objectives. But these multiple objectives are not a fixed set of multiple objectives. It depends on the current situation. And that's why I keep emphasizing from the beginning, it's really about finding acceptable solution. And I try to manage different trade-offs at one time. I think he has another question.
Step up ahead. Basically, have a box where have a values. So the human comes and gives you the environment. Somebody is going to code. Because otherwise, if you end up learning those, values, goals, objectives, these are something that someone has to give to your system. So, otherwise, I can put the values that I want to steal as much money as I can from something.
Yeah. In this case, I just given to you, utility function is actually in this box. Yeah. So this is given by human being. So what I said in the very beginning is this actually can be modified by the internal node as well. Okay, I didn't put this link, and then that's where the monitor, the controller, can be useful. I don't know whether you have thought about this contradiction that autonomous system. If a system is truly autonomous, okay, in theory, then it's extremely scary. Okay, but what we talk about is autonomous driving is actually far more constrained, not entirely autonomous. Anyway, I'm off track a little bit. So, for the time being, these goals, values, objectives, and constraints are imposed by human beings, such that the expression is within certain bounds. They don't do something unexpected.
So it's like a slave, so this becomes a slave based on objectives.
So this is more like setting a boundary and telling a child, don't do this, but in between, you decide what to do.
Let's take the value of the second meter. It's somehow like your training, your knowledge, your abilities. The next time I want to go the region, instead of something like training, I didn't understand exactly advantage. Even like one.
Okay, so in this work, in my implementation, there's no training. Suppose I'm a camera checking an object. I host an auction, and then after winning bidding is received, and then I pass object there. So next time, if an object, I'll do exactly the same thing. Host. So there's no training process, at least in my case. You could actually put in training into it, but in this case, the part of the reason is influenced by our collaborator. They said that real-time performance is essential because people are working. So original background thing was for the intelligence thing. So they want something very quickly in real time. So we didn't use any sort of a training there. Or you don't understand why we need to have this trading process. I pass to object, and I receive the bidding price, and then his utility will be reduced, right? If you don't do this, if you don't pay, then you get this behavior. All the cameras try to get all objects. That's not possible. You want to deter that. So the bidding process, you can imagine, is for resource match. If you don't have this payment system, you can say, then I can bid a very high price. Okay, and then that's not good because you want that bidding to be related to this camera capability. Some camera, very strong CPU, that can bid more. If you don't have resources, you want to prevent it from bidding. You don't want to pass object to a camera which is very weak also further away. So that's why you set the price, saying you can't just bid arbitrarily. I want you to pay a price. That price, the bidding you can bid, is actually proportional to your performance and to your physical distance. So it's more resource allocation issue.
Thank you for the presentation. The first of your presentation, you mentioned one of the advantages of this technique is that we can consider the uncertainty in the application. And I want to ask, do you consider uncertainty in the smart?
Sorry, have I considered system other than smart camera?
Uncertainty, in this example, the smart camera is.
I didn't quite get the question.
Because the uncertainty confirmation, one of that.
Because uncertainty.
Yeah, uncertainty confirmation. In this example,
yeah,
you have this parameter uncertainty.
Oh, uncertainty. Okay. The parameter of uncertainty in my experimental setup is for every camera, I set a parameter in terms of failure. So there's a probability for every single parameter, for every single camera to fail. So this is how I capture part of uncertainty. So I start with a 10 camera or doing simulation 100 cameras. And then I set a parameter for camera, say P, F equals 0.1. That means that there's 10% chance that camera will fail. Yeah, that's how I use these to capture the so-called uncertainty. So simulation will actually take that into account. So on average, you can say every 10 steps, that camera will probably fail once. Yeah. But in reality, we don't set it as 0.1, 0.01. 1% will be more realistic.
So this the scalability, the benefits seem to arise from the fact that you are sending the information to everyone. You are confidence, which that's why you have you don't need one-to-one communication, so you don't have scalability issues, but you're broadcasting, so which is it seems a bit like there might be issues related to security or communication bandwidth and things like that. So it's I mean, I guess that's the trade-off. I guess it's broadcasting seems to be a key component in the whole algorithm.
So you're absolutely right. It is about the trade-off. So that's why I keep emphasizing the trade-off. The most important reason for being scalable is all the algorithm or the decision-making information were based on local information. We don't use any global information. That's first. Secondly, as you said, it's broadcasting. So even locally, I don't even need to know where each individual cameras are. I don't need to know their physical location. I don't need to know their sort of a physical topology. I need to know their logical one from communication point of view. So you rightly said that this is all about a trade-off, because one of the consequences using broadcasting all the time, you flood the entire network, no matter how much bandwidth you have. That's why we need to have this adaptive approach. You do this while building up your online vision graph, and then you gradually reduce broadcasting to only neighbors within your online graph. So there's a period that you probably will flood the system initially, but gradually it will be more and more efficient, but never optimal. Okay.
Let's think about
Thank you very much.